Right, okay. So, welcome to 4 o'clock on a Tuesday. It's been a long day. It's not over yet. So, okay, so we started looking at filters last week, and we got to a point where we were looking at a first order filter. So we'll just quickly recap on what's going on. So our first order filter has one energy storing element in it, and just see if I can call up let's get rid of that pointery thing. So it's got one element in here, and we found out we could obtain a transfer function which we started to recognize as being a one pole feature, with the frequency component being dictated by S in the full scheme, but we could replace that with j omega for a steady state response. We had a look through and did some basic maths on it, and ended up identifying a half power point where the magnitude actually falls to 0.707. So remember, this is voltage, the magnitude, so voltage squared is power, so if we square that we get half, which is why it's called a half power point. So 0.707, 1 over root 2, is an important number in terms of defining features of frequency dependent circuits. And we could also work out where the pole was actually occurring by effectively setting this part of the transfer function to 0, and then working out under what conditions that would be 0, and that happens when S equals minus omega naught. Okay, so it's all sort of basic stuff. And then we had a quick look at this where we got to at the end of the last lecture. We had a look at this pole 0 diagram for our passive filter, and it had the pole off axis, which means that they actually slice through sigma equals 0, so we can't see that that's sigma, but you should know that by now. We can see that we do not get an infinite response at 0 frequency, so this is 0 frequency, this is increasing frequency along here. And so this slice through the plane of sigma equals 0 gives us the steady state frequency response. And that's where we sort of got to. So if you plot this in linear and log form, so we've just taken the slice through here and just plotted that as a standard 2D graph, you can see that instead of going to infinity at frequency of 0, we're starting to flatten off. Because we're only cutting through the side of the mountain, not going over the peak of the mountain, to keep that analogy running. And if we plot this as a bode plot with a log curve, you can start to see that we end up with what would be pretty much a flat bit, and then trending away down here. And this, you can see where you can start to get the approximation of straight lines from on here. So we would just draw a straight line across here and then a straight line down here and say that's roughly what's going on. In actual fact, we've zoomed in on here, and this is the half power point, or the 3 dB point, and that's usually taken at the point at which the flat response is starting to fall away when we look at it on a bigger scale. But you can see even on a log plot, it's not straight lines, it's curving over, so the straight line is an approximation to what's going on, but a useful approximation to do, and we'll see a little bit more about why it's an approximation going forward as well. So that was a passive filter. Let me get rid of me in the picture, just in case it overwrites the words and I don't notice. So that was a passive filter. We can make an active first order filter, and we looked at this quite early on as an integrator. So it shouldn't be a surprise to understand that we've got an integrator. With an integrator we had this infinite response, and we get rid of the infinite response by putting a resistor in parallel with the feedback capacitor, and this instantly, just by inspecting, shows that we get a DC path through this system, which allows us to stop the infinite response going on, so there's no drifting going on. So that's all good. Right. So moving the pole around, by introducing this RC time constant, we can actually move the pole off the axis, like sort of we did with the passive system. So by adding this resistor here, we introduce a pole that we have control over, and the position of this is dictated by the relationship between R and C, in fact RC, as we shall see. So just by adding a resistor, we've introduced the movable pole, and we can put it where we like now. So we can analyse this quickly using the virtual earth theorem, or we can just recognise this implicitly by remembering that this structure is the transfer function is this impedance over this impedance with a minus sign in front of it, and in this case Zin is equal to R1, and Zf is the parallel combination of these two, and so we can work that out by simple terms. 1 over Zf equals 1 over R2 plus 1 over j omega c, which is just j omega c, and then we can simplify that and we end up with that, which allows us to say that the impedance of the this element here, this combined element, is just this, which we can recognise as a single pole function anyway. So the total response then becomes Zf, which is this one, over Zin, which is just R1. So we do the manipulation on that, we end up with the magnitude response eventually of R2 over R1 plus SC R2 R1. It's still a single pole response, but now we're the position of the pole is being dictated by all three components in this case. But if we make R1 equal to R2 and make that substitution, a lot of these things will cancel out, and we end up with a simplified single pole response, which is just dictated by this position CR here. Remember, this is when we've made R1 equal R2 and just called it R. So we can make a single pole response from our integrated circuit, and we can position the pole wherever we like by adjusting the values of C and R. So it's starting to get useful. If we made R and C equal to 1, we end up with a prototype response, which is normalized to a frequency of omega equals 1, and then this becomes a very simple prototype to worry about. It's just 1 over 1 plus S, and then we can scale it by impedance scaling or by frequency scaling or whatever to actually give us responses and cutoff frequencies that we want, given the limitations of a first order system anyway. So it just says here there's an inversion in this circuit that the magnitude response ignores, because this is an inverting amplifier configuration, so there's a minus sign at the output. If we only look at the magnitude, we get rid of that minus sign. So we have to remember that's gone. It's not normally a problem, but if we're only interested in frequency response or magnitude response, it's fine. But if we're more concerned about the time response, we have to remember there's a phase inversion between the input and the output, 180 degrees of phase. Normally not too much to worry about. Right, so that's first order response. It's a bit limited what we can do. We can just really set the corner frequency, and then the frequency response falls away with frequency, but it's not great. We can add extra poles, and we can improve the performance of the system. And one way of doing this is to add another frequency dependent component, such as in this case an inductor, and we can use the following as a sort of a template. There, I mean, you could swap the positions of these L's and C's and all over the places, and effectively they're still going to be second order templates, but we'll look at this one in some detail. So we've got an inductor and a capacitor, so we've got two energy storing elements in here, and this actually has a transfer function that is dictated by this expression, which is more complicated than a single pole expression, and is actually a two pole expression. So it's quadratic. We've got a quadratic expression in S squared, S, and then some numbers there. And so the response of this circuit is given to us by this overall response. And we can match this to the standard second order response with omega c and everything as being in this form. So we would be defining a Q factor, which we'll see comes down to peakiness, as being this. But this is a well-known expression. It's a standard form for a second order system, and there's lots of standard results that come from this. So we will try and squash any second order response into this type of form, and then we can match components, and then we can just use the standard solutions on it. So how do we get to that? Quite often, certainly when I was an undergraduate, people used to just say that's the answer, and it was left up to the student to go away and work it out, and the students, being students, never did. So I've done it for you. So just to analyse this response here, This is a parallel combination, so we would just say that the 1 over the total impedance is going to be 1 over this impedance plus 1 over this impedance. This impedance is 1 over SC, so 1 over that is SC, and then 1 over R is 1 over R. So we can work that out, simplify it out, and that gives us a response, an equation then for that particular part of the circuit. And then it just becomes a potential divider from this impedance and this impedance. And if you then put that into this potential divider equation, so in fact there's an inversion there that follows. Yes, it follows that Z of S is equal to that. So we've already done the inversion there. So we take this impedance, which is this value here, and we say the output voltage is going to be the division of that impedance over the total impedance, and so this is, and it has an impedance of LS, so it's LF plus whatever this impedance is here. So that's where it comes from, and then we have to simplify that down. And if you're good with maths, which I'm not, and you do it properly, you end up with it in this form, which is starting to look like the standard form that we're interested in. So that's how you get to that if you were interested. Should be obvious by now, but I know that it's not obvious for some people. So we can get it into the standard form. So here's just a reminder of what the standard form looks like. So we can now say that omega naught is equal to 1 over root LC by just equating coefficients here, and Q is equal to R over L omega naught by equating coefficients of S over here, and assuming that and that's how it goes. So that allows us to then solve this in standard form, and then we can relate it back when we understand what omega and Q are from this to component values in that circuit. But interestingly, omega naught is an expression in the Q feature, so we need to calculate this first, and then that leads us to Q, but it means they're sort of independent of each other as well. Right. So this is our normalized response if we make omega naught equal to 1. Omega naught equals 1 just gives us S squared over 1 plus 1 over Q times S plus 1. Poles for this occur same as before when this denominator is equal to 0, but it's not quite as straightforward to get that because this is a quadratic. So I'm assuming that you can remember the roots of a quadratic equation in its standard form, which I learnt as being minus b plus or minus the square root of b squared minus 4ac over 2a, where a is the coefficient of this, b is the coefficient of this of s, and c is the coefficient of s to the naught. So that's the standard solution for the quadratic equation. And if you look at this and relate b to being the coefficient of this and a to being the coefficient of this and c, then b squared minus 4ac, which is this bit in here, is actually equal to 1 over q squared minus 4 just by substitution. And so we're interested in when this part of the equation is 0 or less, or becomes negative, because then that gives us some interesting solutions here. So if q is less than about 0.5 in here, or exactly 0.5, then both roots, both solutions of this are real and lie on the negative real axis. So if we put on a pole zero diagram, they'd be just spread out on the axis like this. And that's not really a very interesting solution because it just looks like two first order stages cascaded together, so it's not terribly exciting. We do get some more interest when q becomes bigger than bigger than 0.5, because the solution to that equation then becomes a complex number, and okay, so this is the solution. So this bit becomes negative, so we end up with this being this whole equation turning into a complex number. So the real part of that becomes minus omega naught over 2q, and that's common to both roots, and the remaining imaginary part will be equal and opposite in sign, because that's just the nature of the equation, and are therefore by definition conjugate. And it turns out, if you do the sums then looking at this, that the magnitude of the entire complex number is just omega naught. It describes potentially half a circle, and if we went round here it would be a complete circle. So omega naught becomes the radius of this of this circle, which is an interesting result, because as we should find out eventually, that means that for a Butterworth filter all the poles are located on the radius of this circle, so that just helps us in understanding where poles go going forward. So here's a plot for omega naught equals 1 and Q equals 3, because now we have two things to worry about. And that means the pole, for a Q equals 3, the pole turns out to be quite close to the axis. So remember, if we viewed this from above, we would be seeing the pole slightly to the left on the axis, but it's not on the axis anymore. It's off the axis. If I can draw it. Okay, so that's if you viewed this from above. This is where it starts to get a bit confusing. You would see across here, so you bring this from, oh, sorry about that line, and across there, and then we rotate this round back by 90 degrees to get it into the standard form of a pole zero diagram here. So we've got two poles slightly off this axis here, and we will take a slice down this axis here to give the frequency response. And if we do that, take this frequency response here, we get this response. So we've got frequency increasing, and we've got a response peaking at omega naught and then falling away again as we start to ramp up this mountain. So you can see is if we move this pole closer towards the axis and we had a bigger Q factor, then we would actually get a lot more going on. Likewise, if we move the pole away from the axis, we would go over a lesser amount and we would get a response that is much lower. So this is the aid to visualization. I quite like it. I don't know if it's probably adding a great deal of confusion to everyone out there. So the following is a plot for values of Q ranging from 0.5 to 5. I've done it by LT spice, so you can do that as well if you want to. Omega naught equals 1. So if we put that into frequency terms, that's 0.16 Hertz again. And you can see here we've got the amplitude response showing some of the peaking, and then as the pole moves away, less peaking. But we can also see the phase response as well, as the response changes phase at omega naught. And you can see the phase change is very abrupt for high Q and less abrupt for low Q systems, which is something to bear in mind as well. Okay, so that's all good. So the interesting thing here is if we have control over Q, we have control over this peaking, and so effectively frequencies here are allowed through. Frequencies in this range, if we've got this response, will be amplified, and then they will get filtered away at the same kind of rate going forward. So if we extend the scale a little bit on this diagram, sorry about the creaking chair again, you can see that this is where the straight line approximation comes in, because they always, whatever the Q factor is, it always then tends away to a standard rate, which for a second order system is 40 dBs per decade of frequency. So going up in by a factor of 10 on the frequency gives us a 40 dB change in amplitude. So that's all the same for all Q factors of a second order system. The only interesting part is what happens at this point here, and this is all down to the transient response, or the stability, or the closeness of the pole to the axis, if you like. But as a general approximation, this is where the straight line approximation Bode comes in. People would just plot a straight line here and a straight line here, and they wouldn't really bother about what's going on at this point here. They would accept that it's an approximation, and that they might have to be careful about the peakiness of what's going on at the point there. So the Bode plots do tend to hide a multitude of sins if you're not careful. So, as it says at the bottom, the interesting feature of this becomes the Q factor, or the Q value, and its associated peaking. And peaking just means how pointy this is, how we're doing. So we should note there's a special value of Q of 0.5. This is called critical damping, and in the time domain, which we'll look at in just a minute, is the value of Q for which the system returns to zero the quickest. So systems always have a response time. They always respond to inputs, and that we're obviously interested in those. And if you have a Q of 0.5, the system will recover itself as quickly, or the most quickly that it can. So you could view that alternative responds the fastest to a step input without any overshoot. Another interesting value of Q is 0.707, which is our equivalent of our half power point in the amplitude response. This actually gives us the widest bandwidth in the frequency domain, but allows, or as I allows, has a single overshoot in the time domain. And confusingly, this is also sometimes referred to as critically damped. So you can see it starts to get a bit confusing. So what do we mean by that? So if we look here, we've got Q of 0.5. You can see that the frequency response is decaying away quite early, and so the flat bit of the response, where nothing much is happening, is only from here to here really, because after that it's starting to fall away. Q equals 0.7. We've improved our bandwidth. We've got a larger flat area in terms of frequency before it starts to fall away. And a Q equals 1 gives us a much wider bandwidth, but except it's starting to rise above the normal value of 1 before it falls away. So there's a little bit of amplification, and then as the Q factor gets bigger, it gets a bit mad really. So for a standalone second order filter, it's common to design for the widest bandwidth, as we don't want peaking because that emphasizes frequencies. We want to be nice and flat for as long as possible and then fall away as quickly as possible. So the black line tends to be what we aim for on a second order filter. So even though the complicated maths came into play, really it's quite limited what we can do with a single standalone second order filter in terms of design. So if you're interested in the step response of this, so the time response, so we're not looking at frequency, looking at time now, you can see if you hit something with a step response, the system, so we hit it with a signal coming in, stepping from 0 to 1 volt up here. Different Q factors respond at different rates, and you can see a low Q factor is highly damped, and so it takes a long time to respond, and with different Q factors we get different responses. And so you can see that the fastest response is coming from the one with the single overshoot effectively, which is this one here. And if you had a higher Q, you would see what's called ringing, so this will come up and go down and wobble around, and that's an indication of instability, which is an indication of a pole being quite close to the axis. But the real power of controlling the Q comes when several stages are cascaded together. So we could take a second order system and we can cascade that with another second order system, make a fourth order system, and then we've got 4 poles, and that makes for quite an interesting mountain range. And depending on where we position the poles in that landscape with respect to each other, we can get some very interesting frequency responses. And that's where the complicated maths come in. And as it says here, the transfer function can be expanded to have more poles and indeed zeros, but it starts to get more complicated. But they're useful, and people better at maths than I have done all this and solved the equations and told us what's going to happen. And one of them you've probably heard of is the Butterworth equation. So Mr. Butterworth, probably Professor Butterworth, developed a polynomial that gives us a maximally flat response in the pass band and rolls off towards 0 in the stop band. So if you want a really, really flat response in the pass band, Butterworth filter is the way to go for it. But we pay for this with quite a complex equation. So the Butterworth polynomial is defined as being this. So it's 1 plus omega 2 to the n. So we've got another factor to play with, now we've got n to worry about. Where n is the number of poles, so we can make this whatever we like really, and omega is the cutoff frequency that we're interested in. So in normal form you would see it like this, where we've just recognized the fact that it's omega over omega naught for our normalization function. So these are effectively the same. So if we were to develop a fifth order filter and manage to get that Butterworth equation right, this is the sort of map we would be looking at. So you can see, if we drew this from above, and I would dare to draw it again. So again, we're viewing it around 90 degrees. We've got a pole here, a pole here, a pole here on axis, and then we've got conjugate ones here and here, and this is actually on, well, I'm just going to move over a bit, but they're on a circle if you view them from above. And so again, to plot them on a true argon diagram, we'd have to rotate this piece of paper just by 90 degrees to have a look what's going on, to keep all the poles in the left hand plane. But it's literally just turning the piece of paper around to see. So that's what we're trying to achieve, and if we do that and then we take our slice through the frequency axis here, you can see that we've got a very, very, very flat response despite having all these mountain ranges interfering with each other, and then it falls way down here. So the cumulative effect of adding multiple poles leads us to this flat frequency response, as long as we put the poles in the right places, and that's where the maths comes in. Okay, so if we look at that, we can see this is a log linear scale. We've got a nice flat response, so the linear, even the linear scale is showing us a flat response. Then it falls away and decays away, and we've got no peaking at omega naught, and we've got a nice wide frequency response. And so we've compared that with the best we could do with the second order system, which is, you know, the special case of a Butterworth filter in some ways. It can see that the cutoff is much steeper with a fifth order, so we're going to get 100 dBs per decade on the fifth order, and we get a flatter response for a longer period before it curls away. So the second order does its best, but it's trending towards this, where the fifth order does much better. Higher order filters will obviously then improve and do much better as well. Okay, so we can see the advantages of going up in the order of filter. So the question now becomes, what are the values of the poles for the Butterworth polynomial? Once we've got them, we can put them into our circuit and build the circuit that does it. If we're going to analyse the polynomial from first principles, it's difficult, worth doing once though. It usually starts with the definition of the square of the function we want, as this is a function related to energy. But the real reason for doing that is it allows us to split the function into two later, because we will only want to take half our poles eventually, because we want to keep it stable, keep all the poles in the left hand plane. So that hopefully will become obvious a bit later. So with a bit of manipulation of magnitudes and definitions, we can say that if we have a function g squared of s, which is defined as having the magnitude of h s squared, that is the function of two equivalents of h, but this is this is the conjugate of that, and that's the equivalent of having s and minus s in the functions. So these are what we want to try and do, because eventually we want to be able to get rid of half of these solutions, because they're going to be in the right hand side of the argon diagram and therefore unstable, so we want to get rid of those eventually. So there are several ways of doing it, but we would do it by starting with our definitions. So we would take this as our original equation and just make it equal. If people want the detail of exactly what's going on, there's a little bit of stuff going on down here, but if we just take our word for it and we just say that this function is the equivalent of this, which is the squared Butterworth function that we had originally. Let's see if we can get back to that. We've got that anyway. Yeah, so we've got this function and we square it, so we get rid of the square, so it gives us g squared. So that's h times h, so the square root's gone. That's that function there. And then the idea is eventually we're going to need the square root of it, but we'll keep it in this form to start with. So the magnitude of that is that, which is great, and that leads us eventually to our solution that we're looking for. So which, if we take the square root, is what we're after. So this is explaining how we get back to our original function. And what we want to do is, because the solution to this has poles in both sides of the diagram, if we split it into this function here, eventually when we've got the answers, we can effectively just ignore this, because we take a square root, we don't want half the poles, and we can just keep these poles over here, and mathematically it's still valid. Okay, So probably haven't explained that very well, but it's a trick to get rid of half the poles, and we can choose which poles to get rid of, and we get rid of the unstable ones. Okay, so go back to this again. We need to get the poles from this, and the poles of this are going to be defined when this denominator is equal to 0, which is effectively when this part here is equal to -1. If we say that 1 plus such and such equals 0, then this equals -1. And we have to go back to phasors to get some standard results here. So we can say that if that equals -1 divided by 1 over root n, so we've taken the n from over here and moved it to the 1 side, the definition of -1 to the 1 over n is a rotating phasor with this definition. So this is, if we can think of this as being because the magnitude of e to the j is going to be 1. And that's where it all comes from. So if you're interested in the maths, it should be obvious to you. If you're not interested in the maths, it doesn't really matter. But then you can see that when n equals 1, for example, it just boils down to a single pole. And when n equals 2, we start to get rotating phasors going through, and we can keep going as much as we like. So it's starting to get a bit complicated. But then by taking each of those solutions and looking at them in a bit more detail, you can start to see where the poles come from. And eventually, after much phasor manipulation and just moving around, it's not terribly complicated, but it does require you to sit down with a bit of paper and chase it through, if you're anything like me anyway. You end up with eventually that the plus and minus, there's two poles, remember, become the solutions to this equation. And the one poles that we want are given by sk equals just this part. So we've just taken the half that we're interested in, the ones that give us in the left hand side of the diagram. Right, so there's some words to try and explain that there, which you can look at in your own time if you want to. So it's interesting that the roots are always conjugate pairs if n is even, and if that's the case, we know that a conjugate pair can be expressed as a second order function. We just looked at that. So even if we've got multiple pairs, that just means it's multiple forms of second order functions. So we can cascade second order functions together. And even if n is odd, there are still going to be pairs of conjugate roots, but there will also be just one root on the j-eigenmer axis, which is a first order system. So for example, our fifth order system that we just looked at is made up of two second order systems cascaded and a single order system. So we don't have to worry about designing a fifth order system. It just boils down to being able to design two second order systems that are slightly different and a first order system and cascading them, as we shall see. So for example, in the case of n equals 2, so two poles, the previous slide allowed us to say that the poles we're interested in are defined by this, and we have to go up to n equals 2, so we've got k equals 1 and 2. This will give us two poles which are defined by putting the numbers into this and looking at them. So we end up with this, which by Euler's principle then can be split into this type of form. So this is the cos plus j sine form of the exponential, and that just then boils down to some numbers. So you can see now where we get our complex conjugates from. So we've got plus j 0.707 and minus j 0.707. So these are the poles that are complex conjugates to each other. And if you know they're complex conjugates, you can start to apply some basic identities to this, which allows us to manipulate the standard forms a little bit. If we note that z star being the conjugate is equal to z squared, and z plus z star is equal to the 2 times the real part of z, we can get these two conjugate poles into this standard form, which is starting to look like our second order standard form again, which we can then relate to what we understand about circuit componentry. So you don't need to understand this if you don't want to. I find it interesting to slog through it once in a while just to remind myself what's going on, but the upshot of this is that we can get this into a second order form. So in the case of n equals 2, and we put the numbers in, we can take what we've just got from the previous slide, add our numbers in for the real part of z, because we've defined what that is with n equals 2. We end up with this. which we can then normalize to get into this form like this. And so we've got a transfer function for the Bessel solution for n equals 2, looks exactly like this. So we've got numbers in it, and we can relate this to our second order template, which we've already related to the circuitry. So we can start to, having worked out where the poles are, we can now start to work out what Q is, and then we can work out what L, C and R would be in that circuitry. So here's our second order template that we started with half an hour ago or so, and we worked out its transfer function from looking at the impedances to be 1 over LCS squared plus L over RS plus 1, which we related to the standard second order transfer function with omega naughts and Q's involved. And now we have got some mathematics that allows us to position the poles where we want, and so we can pick components to match the mathematical solutions. Okay, so we did the second order one, so this is the second order polynomial. We developed that, and you can look at the maths if you want to know where it's come from. We can break the polynomials down into more complex. So if we wanted a fourth order system, for example, that's now the combination of two second order functions with slightly different components for Q. This is where Q is in this middle component. And so we're starting to get difference. We're starting to balance Q's now to get what we want. So all these are solutions to the Butterworth polynomial with more and more complexity as we go on. So you can see a 6th order filter is actually 3 second order features. But notice that the Q factors are different in all of these cases. So you have to do this calculations every time you want to do it. But someone's done that for us, so we can look it up in a set of tables. But at least hopefully now you've got some idea of why these numbers are as they are. The more stages you've got, the flatter the response you'll get if you get the numbers right. So if we want to design a fourth order filter, we can take 2 second order stages. We know that now, so it's not as scary as it would have been immediately before. And if we go back to our chart, we're going to be designing for this polynomial or this quadratic, and then for this quadratic. So we're going to have 2 of those template second order filters with the L's and the C's, and we're going to cascade them together to give us this overall response. So that's our polynomial, the first one. This is how it relates to the components of our system, and this is how it relates to the second order template on the. So we can just now effectively say what we're really just trying to say is that we're matching the coefficients. So 0.7654 is equal to L over R, and we're free to choose either an L or an R and relate them accordingly. So let's let L equal 1 for sake of argument, and that must mean then that R equals 1.3065, so that this becomes this is a simple enough equation. And for the second stage we do exactly the same thing. We have the polynomial, we relate it to the transfer function of the circuit, we pick a value for L. In this case I said let L equal 100 because I know that otherwise we're going to have some loading effects. It doesn't matter if we've impedance scaled it. So if you let L equal 100, then R equals 54.1, LC equals 1 because we can just relate the coefficients. S has a coefficient of 1, LC must equal 1 then. We know what L is, it's 100, so C must equal 0.01. Okay, so that's simple enough how to do that. Build the circuit. This is our first second order section. This is our second order section, second order section. Put the component values in. They're purely mathematical numbers at the moment. Run the simulation and you can see we get a very flat response up to a frequency of 1.16 Hertz, and then it falls away. And if you measured this, it would be down at 40 dBs per decade, and it would actually be quite a flat response on this. And the time response or the step response is quite fast acting. There's 1 and just maybe 2 overshoots, but it stabilizes quite quickly. So that's something you can do, and if you get some time you could actually put this circuit into LT-Spice and then try impedance scaling the different sections, because you notice I made it 100, and see what happens when you get the impedance or loading effects a bit wrong. That's the power of the simulator. It's also the power of knowing the maths and also understanding a little bit about impedances. So have a play just to get a feel for it. Right, so that was a passive filter, second order. It's what's called an LCR filter. They do have some advantages, but they have to have inductors to realise complex poles and zeros. We haven't talked about zeros yet, we will do. As a general rule, circuit designers don't like inductors because they look like antennas, and also they have a lot of weight and mass to them in comparison, and so can mechanically be difficult over a period of time. They can break off because of mechanical moments and things. But anyway, so people don't tend to like inductors. They're also difficult to make to known accurate values, so they tend to be expensive. So active filters using op-amps can be used to eliminate the need for inductors. So complexity usually comes into circuits that, because people want to make them cheaper. It all boils down to cost at the end of the day, because you're going to make these things and sell them. Okay, so they replace inductors because they can be used to apply controlled positive feedback at the resonance frequency, which gives a sort of an artificial peak or a Q. And they can be made to have high impedances as well, which means that you can cascade things much easier. So we're going to now look at a very common second order system. It doesn't really trip off the tongue. It's a voltage controlled voltage source topology, VCVS, which is basically an op-amp. Okay, so this uses resistors, capacitors and op-amp to get a second order response. So these are starting to become useful blocks of circuitry, and I think you might have done one with Alex last year, but we'll look at that in a bit more detail. But the limiting factor will always be the performance and frequency response of the op-amp itself. So for very high frequencies, the passive networks that we just looked at are going to be preferred. So for very high frequency RF, you'll still find a lot of passive networks being used. So this is a template for a second order function using an op-amp, and it's called a Sallen-Key network, and it's one that you've probably seen before. So we've got a gain stage in here, so this is a non-inverting amplifier type configuration, and then we've got some frequency controlling components with the feedback being controlled by a capacitor, which is going to be giving us some frequency dependent feedback. So there are two poles because there are two frequency dependent impedances, the capacitances. So effectively we've got two poles in this circuit. So we'd like to do an analysis of this to figure out what's going on. So we can do the same kind of sort of thing we did, and we can apply the stuff we did in the first year with nodal analysis and Kirchhoff's current laws. There's nothing complicated particularly about this. So we can just say that we're going to be starting to look at the nodes. So we do nodal analysis here, nodal analysis here, recognizing the fact that there's no current going into the op-amp here. Which allows us to create effectively the transfer function of this system. So we're looking for V out over V in. Okay, so if you do all that, you end up with quite a complicated equation, but it's come from very simple maths, but includes V1, which is the node voltage at this node here. So we have to get a substitution to try and get rid of that. So you do simple, we've got enough equations, got 3 equations and 3 unknowns, so we can do all that, and eventually you do the sums, do it for yourself at least once on a piece of paper, just to show you where the mistakes can be made. Eventually it leads you to this transfer function HS equals V0 over V in, which is defined by all these components and parameters in the circuit, which is starting to get a bit complicated. But we can compare that with our second order function template, and we can see that we've got a standard second order response here because we've got an S squared, a coefficient of S squared, a coefficient of S and a coefficient of 1. So we can start to relate that to the second order template with omega naughts and Q's in it. And we can see that omega naught is defined as being 1 over square root R1, R2, C1, C2, and Q is a bit more complicated as it involves all the components and also the gain of the stage. So what we'd probably like to do is try and simplify this a little bit. So we put some constraints on. These are arbitrary constraints just to try and make life a bit easier for us. So if we make R1 equal R2, just call it R, and we make C1 equal C2 and call that C, we can show that we can have a very simple control of it. We end up with omega naught cutoff frequency being defined by 1 over RC, so we can just pick values for R and C, make them equal to omega naught, and then Q becomes 1 over 3 minus A, and A is the gain of the amplifier. So we've got independent control of omega naught and Q because they're completely different sets of variables, so that's quite nice. We can set omega naught by setting R and C, and we can set Q just by controlling the gain with the amplifier. But if we go for a high Q, we need to get very good control over A, which can lead to some issues going forward. We could also think of some other constraints. We might want to make the gain equal to 1 for the amplifier, just make it into a buffer. So if we do that, we save 2 components, and that saves us some money. So that's probably not a bad thing to do if we can get away with it. There's some issues if we do that just basically. It gives us a Q of 0.5 if you follow the maths through, which makes it not a very exciting sort of filter system at that point. And that's what's going on through there. But it allows us still, if we then do the sums, we can manipulate things, and we can it gives us a 0.5. But if we use this constraint of R1 equals R2 and C1 equals C2, it gives us very little control over what's going on. So we have to free these up a bit, and then we have a bit more control over what the Q factor could be. So what I'm going to do now, because we're running out of time, is I'll stop that at that point, and I'll explain that a bit more clearly next time, and we'll look at the performance and simulation of these types of circuit, and then we'll look at the problems involved with the Sallen key, and we'll look at alternative structures that are arguably better than the Sallen key, particularly for integrated circuits, and look at those in a bit more detail. Okay, so we'll stop at that point, and thank you very much.